Okay, so this is lecture number 8. We looked at the phase frequency detector yesterday and the frequency detection part. Do you have any questions? You mean to say yeah, yeah, yeah. So, where, in an absolute sense, which phase error will it log to? That depends on the phase error detector. So, like in XOR, it's pi by 2. In two-state PD, it is pi. So, that thing differs. So, yeah, but that is not a problem as such. Means you are still getting a phase lock in the system. Okay, so just to wrap up that part, there is another kind of frequency detector which is counter-based frequency detector, and this is, I think I talked about this thing in the very beginning where I say how can you detect the frequency error. So just a minute, counter-based frequency detector, and this is nothing but you have so let me just say you have two counters. Counter here means that you are counting the rising edge or falling edge, but only one. Okay, and you have this signal as R, and then you have another counter where your input signal is V, and you use both these counter outputs and determine whether one is lesser or larger with after some evaluation signals, and this output will give you what delta f you have. So in a very means we will see how can we implement this, but let's say I am, and this is a R signal, right? And then I have V, which is, let's say, twice the frequency, sorry, half the frequency. So I have, this is my V signal, and I'm counting on R and V in absolute time, with absolute time reference. So whenever I get this evaluate signal, so let's say I get the, if I start here, if this is time axis, I start at t equals to 0, and I get my evaluate signal, let's say somewhere here. We will see how to get the signal exactly, but I get my evaluate signal at this point, and I read my counter values. So my first counter value will read, if the counter on our signal will read n1 is equals to, this is 1, 2, 3, 4, 5, right? N2 will be, it will read 3. So depending in an absolute time, you know this is counting this much, like R signal is counting this much, V signal is counting this much. So what's the delta error in between? Now I drew it in a very like fashion. If I draw it in this fashion, you see that I can always have an error with one clock cycle easily. Right? Means if my counters are, as soon as the rising edge comes, they give me the counted value, they add up to 1. So anywhere I lie between the next rising edge, it still counts as a one cycle. So the error will be like that. Whichever is the smallest period, you will have an error corresponding to that. And these errors are normally measured as, let me just, okay, so these errors are normal frequency errors, is normally measured in ppm, which is delta f by fr times 10 power 6 ppm, parts per million. So what a frequency detector block means, if I am using this kind of frequency detector, I will try to bring the frequency error within, let's say, 1000 or 10,000 parts per million from very large error. and then my phase error detector or phase frequency detector loop will take over. So another way to implement is, so let's say I have my R signal and this is divided by N1. Okay. If this is divided by N1, then the clock which is coming out of my R signal, I'm trying to generate the reference right now with the R. Like what should be my counting period. So, okay. This one is 2 power N1 times R. Sorry. Times TR. Right? Now I use these rising edges, use another block which is a rising edge detector, which gives me signals like this. It just give a very short pulse whenever the rising edge on the input clock comes. Okay, so this is also 2 power n1 times tr, and this, now let me just say, you have another V signal here, and let's say you have something as n2 bit counter. Okay, so this is a reset or some other signal which gives me the, this is logic. So what this logic block is doing, it is taking the divided clock of R. So the time period, it is 2 power n1 times tr. In that time period, it is having two rising edges, means these are the two rising edges. So it looks at the counter value at one rise, like whatever the starting rising edge, then the next rising edge, and it finds how many counts have I done. So you know the frequency. It means if I, so just for an example, if I say between two rising edge, I count something as, let's say, m. If m is the counter value, the difference between the two, right? That means that m times t of v is equals to tr. Sorry, m times t of v is equals to 2 power n1 times tr, right? So did you get this thing? The two rising edges are 2 power n1 times tr away. The rising edge detector is generating a pulse at each of the rising edge. So that is the time difference in which I am counting. My reference is fixed. That's how I am saying that I am using with, I am counting with respect to tr. And within these two rising edges, I count some m cycles of signal v. So m times tv should be equals to 2 times n1 tr, ideally. But you know, you can count it whether you are coming just after the rising edge, even after the later. So those errors will remain, but it will still give you a good frequency error, good approximation of the frequency error. Okay, yeah. Which one? Yeah. So this is divided by n1. It is clock dividing by n1. So wait a minute. This one is clock divided by. So you're dividing the frequency. Sorry, this is n times. I just wrote it as a. I thought in terms of divider, and it's like a n bit n stages counter. So I was doing it that way. So this one will be n1. If it is just a divide by n1, then it is n1 times tr, and this is for a where n1 is clock divider, frequency divider as such. Can you use it as a frequency? Yeah, n1 is the frequency divider. And you know how do you divide the frequency? You know that divide by clock divide by 2, right? Yeah. So if I'm using n stages of the divider, then it will be 2 power n it will go. Yeah, you're right here. So yeah, this is another kind of frequency detector. There exists other kinds also, but we will wrap it up here. The frequency detection. Yeah. No, I just showed you the alternative actual implementation of that. This one was just okay. I'm counting on one with one counter, counting on the other. Then I have a evaluate signal and see what is the difference. Now here I need to get this evaluate signal. How will I get the evaluate signal? So this is one way to get the evaluate signal itself. This is a rising edge detector. So whenever you get the rising edge on RED is nothing but rising edge detector. Okay, you can have a rising edge detector by and the clock and a delayed clock that you can use it for the rising edge detector. Okay, yeah, you can flip RN. Means you keep one as a reference, which you think this is a fix, so that R is fixed. You know what values you are using, but it was the same. Okay, so we have seen the phase error detection, we have seen the frequency detection. So now the thing is, how do we apply this phase and frequency error in the PLL loop? Hmm? So how much frequency error are you going to have in your system? Okay. So let me just say, there are two problems with a small or large value of n1. Means both has a problem. So for example, if your n1 is let's say only 10 in one case, right? And in another case, I have n1 is equals to 1000. Okay. Now you see, I have 10 times tr is equals to some p times tv, and in another case, I have 1000 times tr is equals to q times tv. Okay. So in these two cases, so let me, and p and q will surely differ. Okay. If it is an exact multiple, let's say, means if p is let me just say if tv is equals to 2, sorry, example, so let me just get the example here. If tv is equals to 2 times tr, for example, then you have p equals to 5, right? And even when the means this will p equals to 5 and q equals to your 500, no problem at all. Okay. Now let's say if tv is equals to 2.005 times tr, what are you going to count with respect to p? You will still count 2, either 2 or 3, depends where the edge comes, right? So you are an error with 0.005. Whereas with q, you will, how much will you count? This will be, so let me just pick up a number which makes, this is still 2.05 here, right? What will be this number q? So q is equals to 1000 by 2.005. Sorry, 2.05. Is it? No, no, no. Let me just find here. I just want to pick a number which show you the difference. So let's see. This is easier will be, this is 2. So let me just say, so if I pick up 2.1, so let's say 4.5 by 2. I just want to have some easier number. Calculation gets easier. 4.5, that doesn't go that well. So, okay, let's say 2.5 times this will also give it. So let's pick up this same number which we had, 2.05. Okay. Now this one will be much more accurate. So you will from here you will have this one should be equals to 541 5 2000, right? 10 20,000. So you find this number 41 divided by. So you will see this will have a much more accurate with respect to your frequency detection part. In the first case, you will have, this is 2.005. So actually you will not be having 2. The time period is larger, right? So you will have 1. Depending where the rising edge comes, so the error is more. So if you increase the time for measurement, then you will get the error to a better accuracy. Okay, and that accuracy comes when this is not an integer multiple of the time periods are not integer multiple, means TV is not an integer multiple of TR. Okay, but the problem in increasing that is that to get a certain frequency error, you have to wait a long time. So you do not get the frequency error detection in a counter based method that easily. Okay, so just little bit off the this is not that much used in case of PLLs, but let me give you an example where you can exactly measure it. So let me just show. Okay, so okay, so let's say I'm using here only one period. Okay, but within one period I will show if you measure with a counter in absolute time counter based system, you will not you will measure an error, whereas if you apply some other techniques you can measure an accurate. So let's say this is my reference signal and I am only measuring with this within one period of the reference signal. Within one period of the reference signal I count only one V cycle, right? But there is an error. This is not the 1V cycle because I have this much of error here, right? So what can I do? Can you suggest, if I just want a frequency detection, I do not want a phase locking. So in this case, just for an example, so this is TR, this one is TV actually, and let's say this is some delta T which is lesser than TV. Otherwise it would have counted 2. Okay, if in some manner I can measure, so ideally TR is equals to TV plus delta T, counter measures only TV, means one cycle, it measures in terms of periods, it doesn't measure in terms of absolute time value, right? So if I can measure this delta T somehow, then I can measure the accurate timing, right? So the way which is also used in some kind of digital PLLs is that you have a counter. So let me just give you here. So you have a clock V here which is counted, okay, within certain period. So let's say this is having some reset signal which is coming as a R. Okay, so this is a V. Okay, I'll draw it a little bit more clearly. So I have a counter, I'm writing as count, and this is counting the signal V which is coming in the value, and it is reset with R. You can accumulate or reset with R, right? So this gives me the counted value between two reference periods. Okay, then I have another block which is, you can say, time to digital converter, TDC. time to digital converter. Now, how does it work? That is a later thing which we can see. So, time to digital converter will have two signals, which is R and V both, and it measures the time difference between the rising edge of R and rising edge of V, nearest edges. So now I can measure the delta T with some quantization or some error, and this will give me a much more accurate frequency error detection. Now this one will be limited to the quantization error of TDC, because no matter what you do, you cannot measure the delta T with an infinite accuracy. It might be accuracy with 10 picoseconds, 100 picoseconds, whatever the TDC. So this is also being used in case of digital PLLs, but it's more complicated using TDC. Okay. Any questions so far? So I will hope I wrap this frequency detection part here. So now we have the phase and frequency error detection, and we want to apply or use this error in the PLL loop to correct for the phase and frequency. So let me just start with this. I have the PFD, because this detects the phase and frequency error both, R signal, and the feedback signal I have, which is let me start calling as reference and out signal, and the output of this, which is in case of phase frequency detector, are up and down signals. Okay, and actually here up and down signals are pulse width modulated signals. I will tell why I'm writing it in this manner. Pulse width modulated signals. Here the actual information is in the, I'm just plotting one as a, so we know for some given error you can have up signal as like this and the down is like this for some given phase error. We are not concerned about that phase error. And the information which we want to convert in the loop, because we are looking for a phase error, is this phi error. Okay. So this is the pulse width which we want to convert, means whatever output we are going to use with the loop filter or in the correction loop, we want to convert this information, time information, right? So what are the ways in which you can correct this time information? So we already have, just to complete the loop to show you, we know we had a VCO from the previous, and we have some loop filter. Okay. But loop filter input, we have seen all these loop filters, they are passive or active loop filters. The inputs of all these loop filters is a voltage or current. So we need to convert this pulse width to a proportional voltage or current. Means you can think of charge or something else, but voltage and current are the first thing which comes in the mind. Okay. So let's start with that. That this up minus PFT phase error or PFT output needs to convert it to voltage or current, right? So what can you think about it? Up and down signals. So before coming to the charge pump, so we want to convert, so let's say we go both the ways, try both the ways. I have a voltage source which is switched with up and another voltage source which is switched with down. And I pass that voltage source, I mean there is a voltage, so I'm just putting another as in This is a part of a loop filter. This is not the part of the charge pump itself. And this is a ground. So you see up minus down it is because the way I put the sign for the voltage source. This is something you can say V0 something. Okay. You have R and you have C1. So when up is high, the V control node for the oscillator will basically charge up, and when down is high, the V control node will go down. Okay, and another implementation is so this was a voltage based implementation. The other one is I can do the similar thing using a current sources, I charge pump and a capacitor C1. Yeah. So this is again part of the loop filter. We control, this is switched with up, this one is switched with down. Okay. Right, so you have both the voltage based and this one is current based. This is the phase error conversion to some voltage or proportional voltage or current. Finally, we want a proportional control voltage. It's just the way of conversion. Okay. So, what it turns out to be, it is easier to implement the current based than a voltage based. And means, let me say, that means you can always implement a voltage based also, but it's just the complexity which comes in. Yeah, means I can also have, let's say, active integrator, right? Means I am just showing you one way. I can have this with us up and down, and this will be plus, sorry, this is V0, this is Y minus V0. Even this will, means here I can switch the voltage. It's effectively converting the voltage to current and giving the current to the capacitor. But this one, you see, as soon as I try to implement with the voltage source, in first case I need to have the voltage source. That should be a source, like a something is a voltage control voltage source or a voltage source follower kind of voltage source. So it's more complex to begin. Whereas the charge pump, you see only two current sources switching the current up and down. Okay, so let me just start with an example what happens in case of the current base. So now we start actually this will be a beginning of charge pump based PLL. This is called a charge pump. It pumps in the charge on the capacitor actually. Okay, so let's see how it works. Yeah. Whether we want the average of the up minus down or up minus down average will be something, there are two different questions. So let me just say the capacitor, the integrator which you are going to use, right? The average of up minus down will be done by that integrator. Okay. Now, in a steady state, the average of up minus down will be 0. Okay. So these are, so if your question is that I should first average PFD output and then give that average PFD output to the loop filter. No, that is not the case. In a steady state, the average of the PFD output will be 0. So when we derive any of the gain characteristics, we are looking that, okay, when the things have been logged, what should be the average value? If it maintains, means it's like this. I think the confusing part is I am always using that the average value of the PFD output to show you the gain characteristics. Okay, but that is not mean that doesn't require you to first average physically in a circuit. Okay, that's the difference. Does that clear the thing, right? So I'm looking for this. So think about it. In all the analysis, what we are going to do, we are saying that the loop has settled, means the PLL is locked, and all the analysis which we are going to do with any frequency transformation or Laplace or Fourier transformation, they are in a steady state, which means if there is any small disturbance in the system, how does the loop react? And for that small disturbance in the system, we try to find what is the gain of a block, each of these blocks in a linear region. And the gain of the block is small output, means small input versus and the small outputs. And again, we looked at a steady state performance. Means you give a disturbance to the system, how does it behave in a over a period of time? So means to state it clearly, we do not have to do specifically an average of the PFD output and then feed into the loop filter. Okay. So let's start with this charge pump based PLL. So I will just show how the charge pump actually works. So I have this R signal, then V. So you have up as coming like this, and then down is, right now we are just using like a, I am showing you as only as a small single shot at down, but it will be some, there will be some kind of finite rise and fall. Okay, in both the cases. We will see what are the consequences of that. So now, when up is high and I am using the charge pump, now I want to plot V control. Okay, so let's me plot it V control slightly lower. So assume that the capsule was charged to zero, means discharged to zero, sorry, and it starts from zero, and this is in the circuit so far shown, this is ideal capacitor, and only charge pump current, the ICP current is charging the capsule, so this will be a linear integration, right? And once the up goes low and down is also low, it will hold that voltage, and it will again increase in the next one. So this is how the V control voltage will change in response to the charge current. And if in case the down was low, the same current will be used to discharge the capacitor and the voltage will go down. Okay. So now if this is V control, so let me just write it as a delta V control is equals to ICP times delta T by C1. Constant current is V is equals to 1 by C integral of, I think this for sure you know, I dt. Okay. Now this ICP by C1 delta T itself is equals to phase error divided by 2 pi times T. T is the reference period here. So ICP by 2 pi times phase error into TR by C. I will look each term independently right now. Okay, so you see, so if I just rewrite it, let me just rewrite it. Phase error times ICP by 2 pi times TR by C1. Okay, so you see this term is nothing but the input phase error of PFD, input phase error, right? And the output of the charge pump, so this is the input phase error, and ICP is the current at the output of the charge pump, right? And that current value is integrated with some gain factor over the capacitor C1. So this term itself is an equivalent gain of the PFD plus charge pump. Now the question is, this is linear only in, this is linear to the extent as your PFD is there. Means you say if phase error is more than 2 pi, and then it should be more than 2 pi. This is will not be the, this is only in that range. So the thing is, your phase error detector output resets, right, to the zero. So the means the whole gain of the PFD plus charge pump will be like that. Okay, so PFD plus charge pump, if I just write as a total, then that gain K of PD charge pump is ICP by 2 pi. This is for the simple analysis purpose. Okay, so let's just, yeah, so you can tell me that now. So you see the way I have written is not, this is not a frequency domain itself. Okay, so this is an average current which is going to be integrated over the capacitor. Okay, so now let me just say that what is the Laplace transform of the current of the capacitor, sorry, 1 by S C1, right, which is actually acting as an integrator. So when you convert this to time domain, you will get delta V control. So ICP by 2 pi into phase error, right? And phase error is 2 pi delta T by T. Got that thing? So you write the whole transfer. So let me just write it as, and then we will see. So I think the problem is when I write as delta V control, you start thinking this as a Laplace, because I'm talking of gain factors here, right? But this is still a time domain picture, where an average charge is being dumped over one reference cycle on the capacitor, and what is the delta V change. If you want to use the gain factors with capacitor, you either write differential equations or you do the Laplace domain translation. So let me just do that. Okay, so better to write it as like this. Let's say this is your phase error detector, Phi in, then your charge pump, CP by 2 pi, and your only capacitor which I'm using right now as an integrator, SC1, and this is your V control node and VCO. Okay, so this is V control, phi out. So here is your phi error. So the gain of, means I'm just writing this as positive and this as negative. So your V control of S is equals to ICP by 2 pi into 1 by SC1, okay, times phase error. of S. Okay. Now let me just say that V control of S for an input phase error step, phi error. So that is phi E of S is equals to, let's say, some delta phi by S, right? Now what I have, ICP by 2 pi 1 over S C1, and we are considering all these things in one reference cycles. So one other problem which we will deal later is that these are all sample system, okay, and I am using these sample, I am using a Laplace domain for these sample system. So we'll see to what like when we approximate a sample system to a Laplace domain, right, there are something which I am right now just neglecting completely. We will look at that, how these translation come, like because you see here I am integrating only for one time period, but I am still like neglecting, oh, there is no aliasing, there is nothing, and I am still able to use 1 over S easily. So this one is delta phi over S, so which is equal to ICP by 2 pi 1 over delta phi by C1 into 1 over S square. Let me write this is okay. So can you tell me what is V control of T? ICP by 2 pi delta phi over C1 times T, right? What this T should be? No, T is not there. So we have considered, so if you look this one, right? Here in this term, I consider this as an average current over one time period. Means yeah. So now when you are considering an average current or average phase error over one time period, right? This is not delta T here. We are integrating means if you are looking in that term, you're saying whatever the average value at the input you have, you are integrating that average value over one time period, means over one time period itself. Means this is confusing that whether it is T or delta T or TR, this is the relation between when you consider the from the sample system you come to the Laplace domain one. But if I say you can consider that whatever the phase error we have got, right, I can have that phase error divided by 2 pi. Phi E is the phase error, actual phase error. I am taking an average of that phase error over 2 pi, and I am integrating a current proportional to that over the whole time period. So see, whether you integrate phase error phi E only for delta T, or you are integrating the average over the other part. Okay. So this term will be your TR. So does that clear that when I am writing TR by C1 here, and when I go with the Laplace domain and I get the same TR? Any questions? Right? Yeah. Yeah. So that is what. Okay. So let me just go through it again. So in this expression, this is so you got this. This is the absolute expression. There is no problem in it, right? Now I write delta t as phi error by 2 pi into tr. This is the same thing as delta t, right? That is the phase error phi error average over 2 pi, integrate average over 2 pi multiplied by tr times. You can think of that way. I'm not saying, I mean, this is just realizing these parameters. So I can have the phase error, I integrate only over, means absolute time is delta t remains the same, but I can think of phase error average over 2 pi, and that is integrate, that is for the time t r. Okay, so I I will see if I can explain it in another manner which makes it more clear, but this is working in an average sense. Okay, so the sorry means there is no discrepancy between when you start with an absolute time domain picture and when you start with the frequency domain picture and calculate the time domain back. The only relation which you need to understand is that the pulse width, the phase error which was in the pulse width, that phase error has been averaged over the one time period, and a charge pump, the current from the charge pump is integrated for that value. Okay, so let me say if I have ICP, I integrate ICP times delta T. This is the total charge, let's say Q1, right? And I can also say this is ICP averaged over, let me just put it as a, is there any difference in this? No, right? And what is this? Now, phase error is 2 pi times delta T by T, okay? Which implies, now coming back to this expression, Q1 is equals to ICP by 2 pi into phase error times T. So the relation is that the charge means in an actual the charge which you only pump into the capacitor for a delta t time, you can always think in the analysis term this is average over the whole time, means the charge is lower but you integrate for the whole time. I am looking at the final control voltage means as such. I am looking for, so in, so if you see the Laplace domain one is what we are considered is what is the, you have a phase error output, how much is the change in the control voltage. So we are looking for that delta V part. So that is what we are not looking how it is, how it functions throughout this period. Means I at no point I have talked what is in between. I'm only looking what is the final one, and I am looking so that I can have something as a not a piecewise linear or not a discontinuous thing, right? I'm looking for something as a continuous. So what I'm writing it here in terms of loop gain means if I try to, so let me say if I try to write the Laplace domain transfer function for this, okay, you will see that this will be a more complicated one. And what we are concerned only in the, and here the thing is we are concerned only in the changes which are coming every reference cycle. So that is the thing. But whether it rises slowly, it rises fast, how does it rise, how does it fall, that is going to affect your transient nature of the PLL. It's not that this is not going to affect. This is going to affect and we will deal with this. But for the analysis purpose, we are looking at an average or changes in reference periods. Okay. So let me, okay, so let's stop here. We will start tomorrow and complete this part.